3 million kilograms of rocket. That is what it took to send 3 human beings to the moon and bring them home. 13,000 times the astronauts' combined weight, 91% of it fuel, stacked 36 stories high on a Florida launchpad. Then, in December 1972, Apollo 17 commander Eugene Cernan climbed the ladder back into the lunar module for the last time, and nobody went back for over 50 years. Not because the moon is far. At 384,000 kilometers, a radio signal completes the round trip in under 3 seconds. The moon is close. The problem is one equation written in 1903 by a deaf, self-taught schoolteacher in rural Russia that imposes an exponential tax on every kilogram leaving Earth, a tax so punishing that even the wealthiest nation in history eventually stopped paying it. That equation explains why humanity abandoned the moon. And it explains why the first crewed moon mission since Apollo has to be built in a way that would baffle the engineers who designed the Saturn V. The schoolteacher was Konstantin Tsiolkovsky. The rocket equation bearing his name governs every launch vehicle ever built. It says a rocket's achievable speed depends on how fast its exhaust exits the engine and the ratio of its full mass to its empty mass. Straightforward until you meet the logarithm hiding inside. That logarithm makes the fuel cost of increasing speed grow exponentially. Doubling speed does not require twice the fuel. It requires squaring the mass ratio. Tripling it means cubing that ratio. For chemical rockets, the only kind powerful enough to escape Earth's gravity, this forces 85 to 96% of launch mass to be propellant. The crew, the science, the mission, everything that actually matters, that is the tiny remnant perched atop a controlled explosion. This single principle explains everything that follows. The rocket equation turns velocity into mass, mass into fuel, and fuel into a problem that compounds exponentially. Every decision in 60 years of lunar exploration traces to one question. How do you work around this equation? It cannot be written, only cheated. And the engineer who found the most important cheat was not Wernher von Braun. In 1961, a mid-level NASA engineer named John Houbolt realized the leading plan for reaching the moon was physically impossible and could not get anyone to listen. The plan was called direct ascent. Build one colossal rocket, fly it to the moon, land the whole vehicle on the surface, and fly it straight home. Clean and intuitive. Houbolt ran the numbers through the rocket equation and found it would require 12 to 15 million kilograms on the launchpad. Nothing that massive could be engineered within a decade, perhaps not ever. The equation makes the problem brutally clear. Landing on the moon means decelerating from orbital speed to 0. That takes fuel. Launching again for the return means re-accelerating, more fuel. But every kilogram of return fuel had to be slowed during landing too, demanding more landing fuel, which in turn had to be launched from Earth. The costs cascade through every stage, compounding exponentially. Houbolt's solution was counterintuitive. Do not land the whole spacecraft. Fly to lunar orbit in one vehicle, send only a tiny stripped-down lander to the surface. After the moonwalk, the lander's ascent stage, just the top half, deliberately shedding landing legs and the descent engine like dead weight, climbs back to orbit, docks with the main ship, and the crew transfers over for the trip home. This was Lunar Orbit Rendezvous. Prediction time. By leaving the heat shield, service module, and transit supplies safely in orbit, instead of dragging them to the lunar surface, how much launch mass does this approach save? Most people guess something meaningful, 30, maybe 40%. The real answer, a factor of 4 to 5. From an impossible 12 million kilograms down to roughly 3 million, the exact mass of the Saturn V as built. Houbolt did not rewrite the rocket equation. He changed what the equation operated on, ensuring only the minimum mass descended to the surface and climbed back out. Because the exponential penalty compounds at every stage, reducing mass at the costliest velocity change sends savings cascading backward through the entire rocket, shrinking every prior stage dramatically. If that clicked, if you see why cutting mass at the most expensive phase produces disproportionate savings at every earlier phase, you now understand the most important principle in spaceflight architecture. Every mission design since Apollo, including the first crewed moon mission since Apollo currently being assembled, descends directly from this insight. But Houbolt could not get anyone to agree. He was associate level, not management. He wrote memo after memo and was ridiculed. One senior figure reportedly called his concept preposterous. In desperation, he broke every protocol and wrote directly to Associate Administrator Robert Siemens, bypassing his entire chain of command. The letter opened, "Somewhat as a voice in the wilderness, I would like to pass on a few thoughts." It should have ended his career. Siemens read it instead. Independent studies followed. By July 1962, following Werner Braun's crucial endorsement weeks earlier, NASA officially selected Lunar Orbit Rendezvous. Without one stubborn engineer's refusal to accept an impossible mass budget, Apollo almost certainly would not have reached the moon by 1969. The vehicle his architecture made possible remains the most violent machine human beings have ever successfully operated. 5 F-1 engines on the Saturn V's first stage, each consuming approximately 2,600 kilograms of kerosene and liquid oxygen every second. Combined thrust at ignition, roughly 34 million newtons. The sound exceeded 200 decibels at close range, past the threshold where acoustic energy stops being noise and becomes a physical weapon. Eardrums rupture, internal organs vibrate against the ribcage. Engineers built a massive water deluge system that dumped hundreds of thousands of liters onto the launch platform in seconds, not to muffle the sound, but to deflect the flames and shield the pad structure from thermal destruction, because at 34 million newtons of thrust, unmanaged exhaust would melt through steel and concrete before the rocket cleared the tower. 13 metric tons of propellant disappeared every second. The first stage burned for roughly 150 seconds, and by separation, the Saturn V had shed about 80% of its total mass. A 36-story tower eating itself alive in 2.5 minutes, converting its own body into velocity, the rocket equation made violently physically real. Across 6 successful landings, Apollo 11, 12, 14, 15, 16, and 17, 12 human beings walked on another world. 12 out of the roughly 100 billion humans who have ever lived. The rocket equation made each one the rarest kind of explorer in the history of the species, rarer by orders of magnitude than anyone who has summited Everest or reached the deep ocean floor. Each mission launched approximately 3 million kilograms from Florida and returned roughly 5,500, the command module and crew, a ratio of more than 500 to 1 between what left the ground and what came home. Then the program ended. Apollo 18, 19, and 20 were cancelled. The Saturn V production line was dismantled, tooling archived, the workforce scattered. By the late 1970s, the rocket could not have been rebuilt even with unlimited funding. The institutional knowledge and supply chains had evaporated. Apollo had chosen brute force, 4% of the entire federal budget, year after year, directed at a single program. The rocket equation demands either brute force or cleverness, and when the brute force funding dried up, so did the moon missions. For half a century, no alternative architecture existed that could solve the equation affordably. So, second prediction. Given the equation's tyranny and Houbolt's principle that each phase should carry only the mass it needs, what would the first crewed moon mission since Apollo look like? How far could engineers push that principle? The answer is genuinely radical. NASA's Space Launch System generates thrust comparable to the Saturn V, but SLS alone cannot land humans on the moon, not for lack of power, but by design. The Artemis architecture deliberately fragments the mission into more specialized pieces than Apollo ever attempted. SLS launches the Orion crew capsule toward the moon. Orion carries no landing engines, no landing legs. It is purely a deep space transit vehicle optimized for crew survival and Earth re-entry. A separate spacecraft entirely, SpaceX's Starship human landing system performs the lunar descent. And here is where it gets extraordinary. Starship cannot reach the moon on a single launch, so it flies to low Earth orbit nearly empty and gets refueled there. A fleet of tanker vehicles, perhaps 8 to 16 separate launches, each deliver propellant to orbit and transfer it into the waiting lander. Only once fully loaded does Starship depart for the Moon. This attacks the rocket equation's most brutal feature head-on. The equation punishes carrying fuel to carry fuel. Orbital refueling resets that calculation entirely. The mass ratio that matters becomes orbit to Moon rather than ground to Moon, eliminating roughly 9 to 10 kilometers of velocity change. Through the exponential math, that reduction translates into enormous savings. This is Houbolt's principle evolved one generation further. Do not carry the whole ship to the surface, and do not carry all the fuel off the ground at once. If that logic tracks for you, if orbital refueling resetting the equation's most punishing term makes intuitive sense, you have grasped the engineering revolution behind the next era of human spaceflight. Most reporting on the Artemis moon mission frames it as nostalgia or politics. It is neither. It is a fundamentally different answer to the same merciless equation. The Gateway, a small station planned for near-rectilinear halo orbit around the Moon, extends this approach further, serving as a permanent waypoint where supplies and equipment can be staged. By segmenting the delta-v budget so the equation operates on smaller masses across shorter velocity changes, Gateway reduces the exponential penalty at every remaining stage. As of 2025, the next milestone is Artemis 2, a crewed lunar flyby, sending 4 astronauts farther from Earth than any human has ventured since Apollo 17 in December 1972. No landing, a demonstration that Orion can carry a crew to lunar distance and bring them home safely. The first crewed lunar landing since Apollo, Artemis 3, targets no earlier than 2027, contingent on proving orbital refueling at scale. That capability, transferring cryogenic propellant between vehicles in microgravity, has never been demonstrated at this magnitude. It is both the highest risk element of the architecture and the most transformative. Because if orbital refueling works, it reshapes far more than moon missions. Consider this. Earth's escape velocity is 11.2 kilometers per second. The Moon's is 2.4. Those numbers appear about 5 times apart, but run both through the rocket equation and the gap explodes. A chemical rocket escaping Earth needs a mass ratio near 40 to 1. Escaping the Moon requires barely 2 to 1. Launching a given payload from the lunar surface costs roughly 1/20th the propellant of launching it from Earth. Sit with that for a moment. The crewed facility on the Moon, once established and supplied, becomes a launch point for the inner solar system, Mars, the asteroids, Venus flybys, at a fraction of the energy Earth demands. The same equation that makes leaving this planet almost impossibly expensive is the equation that makes leaving the Moon almost trivially cheap. Earth's gravity well is the prison. The Moon is the first step beyond the wall. Final prediction. If Apollo answered the equation with brute force, and Artemis answers it with logistics, what follows? What is the logical endpoint of an engineering philosophy built around segmenting the rocket equation into survivable pieces? Permanent infrastructure, fuel depots orbiting Earth and the Moon, mining of lunar water ice at the poles, processed into hydrogen and oxygen propellant on site, manufacturing in a gravity well the equation barely punishes. The true purpose of the first crewed moon mission since Apollo is not the Moon itself. It is stress testing whether distributed logistics can transform the equation from an impassable wall into a manageable toll. Every Starship tanker launch tests it. Every Gateway module advances it. Every Artemis landing proves or disproves it. Tsiolkovsky, the deaf schoolteacher from Kaluga who derived this equation in a log cabin, who never witnessed a rocket launch, who imagined space travel decades before the first aeroplane left the ground, wrote words that now read like prophecy. Earth is the cradle of humanity, but one cannot live in a cradle forever. He understood mathematically both the prison and the key. A single equation encodes why leaving Earth is exponentially punishing and why everything becomes achievable once the escape is made. Over 50 years separate the last boot print on the Moon from the crew now preparing to return. That gap was never a failure of imagination. It was the time required for engineering to evolve from overpowering the rocket equation through sheer scale to outmaneuvering it, for orbital refueling, reusable vehicles, and modular architecture to mature from concepts into hardware. The Moon has not moved. It sits 1.3 light seconds away, a radio whisper from Earth. And the equation between here and there is exactly as merciless as the day Tsiolkovsky first scratched it onto paper. It does not negotiate. It does not care about budgets or ambition. It asks one thing: how much mass are you willing to leave behind to push the rest forward? The first crewed moon mission since Apollo is the first serious answer to that question in half a century. And whether boots press into lunar dust once more, or whether the Moon finally becomes what the equation always promised it could be, not a destination but a doorway, depends on whether this generation's cleverness can finally outpace the exponential. Like if this was interesting, hit the subscribe for more and turn that notification bell on.